my side to everybody else. Just a brief word about PROTOS and who am I. PROTOS is a company. We are specialized on developing domain-specific languages, tools for embedded systems, so software tools, code generators, and so on, test tools. That's what it's mainly about today, and software architecture, always in the field of embedded systems. Who am I? I'm an aerospace engineer who likes embedded software architecture, tests, and tools. And I will lead you through the presentation today. And at the end, I will make a little live demo. So why are we doing what we're doing? Late testing is a real problem, and it gets bigger and bigger the further you go into the process. So for example, a unit test is fast, simple to do early in the process, but already an integration test, hardware software integration test or system test are usually very late in the process, and they can be really expensive, and usually the response time for such a test is really slow. So what we do is usually we bring hardware software integration test and system test to the desktop of the developer, especially for product lines. That's a really important thing to do. The faster you find out where your problems are, and the faster you can retest, the faster you can develop, and the better the quality gets of your overall system. So we need to learn and test earlier. That's what it's all about. Now let's start with a closer look at the types of variability you usually have in your systems. So there are two different types of variability. There's the so-called negative variability. So you build in everything and exclude parts you do not need. So for example, you flash your complete code on your embedded system, and you have a configuration where you can activate or deactivate parts of your software functionalities or whatever it is. That's called a negative variability. The positive variability is you only deliver what you need. So you include only the parts you need in your software. You leave everything else out. That's a little bit hard to do in many embedded systems because you have to deliver them, and in many cases you cannot change them where you install them. So usually in many embedded systems you prefer a negative variability. The point is, if you use a negative variability, you have a higher variability and complexity, not only in your application, but also for the tests. So that's very typical for many embedded systems. So if you can activate and deactivate functionalities on the fly in the field, then theoretically you have to test all the combinations of those functionalities, whether they work together or not. So this brings a lot of complexity into your development and especially into the testing. Usually with a positive variability, you have a lower variability and complexity for tests or also for development. And in the combination, you can, for example, with a product line, you can combine those two types of variability. So I'll get to this a little bit later. So we try to strive for positive variability, but there are constraints that usually lead to a negative variability in your embedded system. So next type of variability is you can have data configuration variability. So you change data in order to change, for example, curves in your or behavior in your sensors or things like that. Then you have structural variability, so different structure for variants. That's usually more complex. So you turn on or turn off a certain building block in your software. That's a typical structural variability. And last but not least, the behavioral variability. So you have different behavior for different variants. And that's very often the most complex variability type, because in many cases the behavior goes from top to bottom in your application. So you change the graphical user interface for a certain variant. You need to change the behavior in certain building blocks, and also maybe even in the I/O structure you need to, or I/O wiring, you need to change between different configurations for your variability. So this is very often a very complex variability. So one idea, just to give you one best practice, often you can replace behavior by structure for the variability. So in many cases, complex behavioral variability can be replaced by a simpler structural variability. You usually need a little bit more fine-grained or finer granularity in your system. And so it's easier to turn on and turn off a complete building block than to switch between different types of variability on behavioral level in all your components. It's also much easier to test. So in order to, if you have let's say only a couple of variants, yeah, you get away without a product line. But what's now a product line? If your variability gets bigger, much more complex, like for example, you have like the car manufacturers, you have many different types of cars, then usually you take a more strategic approach with a so-called product line engineering approach. So the idea is you have all the features in a feature construction kit, whatever this looks like. And then instead of creating all those variants for all those different cars, first you introduce product families and product platforms. So by doing that, you can cluster and pre-select dominant features. So for example, certain car family, for example, the sports car product line of a certain company, all the sports car in one product family, all the let's say vans are in another product family. So you pre-select dominant features, and in the end, the real product can only be configured based on the features the product family pre-selects, and then the fine-grained configuration defines the product between van type 1, van type 2, and so on. And then the customer in the end can select his based on the product family, his features. So it's a strategic approach to variant handling, and it reduces the variability by clustering features into families or platforms. Sometimes you even have more steps in between. And it leads to a massive reduction of complexity, not only for testing, but also for development, organization, production, and so on. So that's the idea of product line engineering, but it's still a variant handling concept. Now let's have a look at an example, feature model example. It's a feature tree, feature model for a certain embedded system. So for example, you could have variants for microcontroller hardware. So in some cases, you might have an STM32 for another product variant, other processor, an Oryx or a DSPIC or whatever it is. Then we could have variants on voltage levels, 3.3, 5 volt, 24 volt, or whatever it is. Then you might have different product variants for different markets or product families, product lines. Then you could have different motors, a BLDC motor, a DC motor. The motors could have different sensors, Hall signals, or a shunt, single shunt, dual shunt, whatever it is. Then also the temperature sensor could be based on an ADC. In another variant, you might have an SPI attached to the, or a temperature sensor attached to the SPI bus. Also bus protocols, LIN, CAN. That's very often, this very often depends on the application you're building your component into, and so on and so on, and all those behavior variants. So that's just to give an idea on which level certain things can vary in product lines. If you make bigger product lines, you might have very similar problems. Now, let's have a look at the testing topic. On which levels can I test variants? The first two levels are unit tests, for example, single C modules, classes, and so on, and also software integration tests. That's also usually done with a unit test tooling. That's easy to automate. That's software unit tests are usually good to write, easy to write, and good to automate, and so on. Then the next level would be our mini hill, for example, the smallest possible hardware in the loop test. That's on a microcontroller level. So the microcontroller as a black box with all the software units, application level, but also with the drivers and so on. Then the next step would be a bigger hardware in the loop test, including a complete control unit with power electronics, with sensors, actuators, and so on. And the last level would be a real system test. So you really test your system. So you get into the car, drive around the corner, or you let the pumper run, whatever application you have. So now, on which level can I test variants? Very good. So on the pure software level, so unit test level, it's very easy to test variants, or at least not so hard to do, because you have the complete code there, and you can run all the tests on software base level. So it's usually easy to test variants. The problem is you can only test on software component level. So this gives you a certain coverage, of course, but you still might have a lot of errors on the integration or system level. Then the really hard thing to do is to go on system level, so with a hardware in the loop test or a system test, because it's hard to test variants if you need different hardware in the loop. So you have different electronics or even different mechanics for certain variants, and that's really hard to do, and it's very hard to automate because you need to switch the hardware between different motors, for example. And the path in the middle would be this hardware-software integration test. It's very good to test variants on application level or also on driver level by simulation of the hardware environment. You still have the electrical signals, but everything else around it is simulated. So you can easily switch, for example, between different motors and so on. So now let's have a look at how we get from a driver test to an application test level. So you could, for example, test only the drivers or the microcontroller abstraction layer for automotive purposes. Then the next level would be a basic software test. So basic software is the reusable part of your software, lower levels of your software, so between your application and the drivers. And the highest level would be a hardware-software integration test. So application level test, but including the basic software and the drivers. So that's the smallest possible hardware in the loop test on microcontroller base. So the idea is here to test at the pins of the microcontroller, but the complete software stack. Now, how do we do that? From a hardware perspective, we use our mini hill board. So the idea is, the blue one is the mini hill board here. We test at the pins of the microcontroller, so that's the system under test here. We connect the pins of the microcontroller over this patch panel with our test system. And now, since it's only wiring here, we can switch easily between different variants on that level. And one level further up, you need, of course, software to simulate the complete environment. So, for example, you need, in order to bring your system under test into the right state where you actually can test, you need to simulate a motor, because if the motor is not attached, you cannot really run your system because it fails immediately. So we test we simulate the motors, the sensors, the complete environment. It's not as hard as it sounds, but that's the biggest part of hardware loop testing, is always to build the environment simulation to make your application believe it actually lives in reality, and it controls a real motor, a real battery, and a real sensor, things like that. So on that level, we connect the typical low-level IOs like digital, analog, all the low-level bus systems, SPI, I2C, CAN, LIN, field bus systems, and so on. So that's how we do the hardware approach here. Now let's start with the lowest level. If you have different microcontrollers, you need, of course, the different microcontrollers in the loop. That's why I have different adapters for various microcontrollers. If you have the same microcontroller, then you need to think about the wiring. Now let's have a look at different wiring options. So together with Hitex, we've developed MCAL and driver tests for Oryx processors. For example, for the AUTOSAR basic software stack and for the MCAL stack. And the first version looked like this, because an MCAL test, there you need all the combinations of all the IOs at every pin. That's a lot of wiring. And let's say an application level test is simpler to wire, but an MCAL level test, especially for ASIL-D, for high safety requirements, that's really hard to do from the wiring perspective. That's why we developed together a switchboard to really switch between all the pins of the, in this case, of the Oryx processor. It looks much cleaner that way. So from chaos to order. But that's only necessary usually for MCAL tests. For application level tests, it looks it goes out of the box. So that would be the wiring approach. Then one very important thing about variant testing is if you have a lot of different variants, it's really hard to automate this on your desktop. You might have different processors. You have a lot of different variants. The tests usually take a little bit longer. So it's very important to have automation. And that's why we use continuous integration. So for example, every commit of every developer, no matter where he sits, is automatically built and tested for all the variants on those different mini-hill boards in the continuous integration server rack. So the same test works for Oryx, for ST processors, STM32, for example, and so on and so on. So that's the idea. Usually you do not run variant tests, extensive variance tests on your desktop. So every code change for all the variants on all targets are tested within minutes or hours, depending on the application. Now, let's have a look at the software side. Now, we have those variants on the processor layer, but the next layer would be the IO layer, so the signals. You have different configurations. For example, at the same pin for one variant, there might be an SPI bus. For another variant, there might be a UART. Or I have for one variant, I have a BLDC motor. For the other one, I have a DC motor or a single shunt motor control or whatever it is, and they might have different wiring. So the first thing is usually we switch the wiring in software. When we start the test case, we switch the wiring. So you have the configuration of the signals for this next version or for this next variant. So then, for example, for the temperature sensors, we can switch between, let's say, an analog value, a DAC, or an SPI-based temperature sensor. We can switch this wire here. That's a pure software solution here. Then for the bus systems, we can switch, for example, between a UART, a LIN, a CAN, whatever it is. Then motor simulations, we can switch between DC, BLDC, field-oriented control, and so on, always based on the same test cases. And in the end, the most important part here is to standardize the interfaces two certain classes of sensors. For example, a temperature sensor should always have, for the test case, that's the test case here, should always have the same interface, because if not, you cannot switch between those two temperature sensors, and also the test cases will not work for different sensor types. If you have standardized the interface, you have a very good chance to standardize those tests. Of course, a LIN might have another functionality than a UART, or a BLDC simulator another functionality than a DC simulator. In that case, you define a standardized motor simulation interface for the standard test cases for all the motors. Many test cases can be standardized by that, by doing that. And then you may create an additional interface, for example, for a specialized functionality for the BLDC test case or for the DC test case. But it's usually a small subset of all the test cases that is very specialized. And you run this extra in this variant test. But we always try to standardize the test cases by using the same interfaces. For example, in this case, we can directly switch between temperature sensors because they have the same interface. In this case, we have an adapter that reroutes the functionality to the simulator of a certain motor type. And here on this level, we can standardize the interfaces, because on this level, that's hard to do. So we make an indirection here in the middle to reroute the simulation information. Okay, now I have my IOs, my simulation environments. Let's have a look at the test cases. So for all the variants in the test cases, we usually use so-called state transition tests. So we can write test cases for all the variants and have a very structured approach for this. So the idea is you define the different variant configurations, for example, in your test cases. You start your test case with defining a certain variant, and then you define all the paths through your application. So turn on the motor, stop, change direction, reconfigure, whatever it is, and you define all those paths through your application by defining an external black box behavior for your application. So that's not the state machine in your application. That's a state machine you use to define the combinatorial tests for variants, for data, and for paths. And every path from initial to end is a test case. So, for example, this way, variant 1 requests speed 10% and so on. This would be one test case. So now the interesting point is you want to cover all transitions here and all states. That's the smallest part here. So you need at least a couple of test cases to really cover all those paths. And we can also cover combinations of paths, for example, to cover variant 1 for all the speeds and all the paths through my application here. And with the test case generator, we generate not only the documentation, as you can see here, but also in SC code, all the test cases that are directly executable. So you have a formal description of the expected black box behavior of the systems for all the variants. And then we have a test case generator for all the variant path and data combinations. That's a very deep testing, and it helps a lot with your variants, but also with things like sporadic errors like race conditions and so on. That's a very good approach for this. Now I'm going to jump in my demo. I'm going to explain you a little bit how we do this from a software perspective. So that's, for example, a typical system with a BLDC motor control. So we have here the I/O layer. We can switch this easily to other I/Os. Here, for example, we have an analog adapter for the motor temperature. This could easily be replaced by a SPI interface or whatever it is. I kept this simple here. So the motor temperature is converted from degrees Celsius to an analog value. You have a digital adapter, UART adapter. Here the duty capture unit with to measure the PWMs. PWMs go into the motor simulation that really makes a closed loop simulation of your motor. And then the motor calculates, for example, 20 with 20-30 kilohertz. It calculates the new speed based on the PWM measurements and informs the whole generator about the speed it needs to simulate. And the whole generator has 3 digital outputs. You can model those simulations as state machines, as Simulink blocks, and so on. Also as C code and so on. But then we generate the complete system. And the last thing we need is the test cases. The test cases are again based on a language that integrates here with the test system. And for example, if you have define your steps and sequences, asynchronous steps and sequences, for example, to change the motor speed, to verify the motor speed in the simulator, and so on and so on. You can also define the switch between the IOs here in those steps. Then you integrate those steps to sequences. So for example, that's a sequence here that uses a couple of steps. You can see you always get the documentation here. That's also very important to really know what test cases are executed and what they look like for certain variants. So that's how we define, let's say, linear test cases, so step-by-step test cases. But now we want to have a look at the variant test cases. Let's have a look at the variant test cases for certain variants. So let's, I've configured the state transition test here in the way that we configure 2 variants. So variant 1, variant 2, and we set certain equivalency classes for certain speeds. So 10%, 50, 90% of the speed. I could also add, let's say, 1% and 99%. As you can see, the documentation is updated immediately here. So, and now I'm generating the test cases. So now let's generate the test cases and run them on your target. So I need a couple of test cases here to do this. So you've seen I updated the test cases. Here you see those are the variants that are needed to test on a very low level of combination. So in this case, every transition is tested once. So it's transition and state complete, the test. And now if I want to execute the test case, I can switch to my graphical user interface. I connect. Here you see all those variants that I generated. Now I start the tests, and while I'm running the tests, I'm pulling a plug here. And now to introduce an error, that's the UART cable here. Now I have an error here, and now I repair the system again. As you can see, I ran all the normal test cases, so the scenario or feature-based or requirement-based test cases, and here I run all the part of the variant test cases. So here you can see the problem I've detected in activate motor control. The UART did not reply. It's clear because I pulled the cable. So now I click on the graph here, and I immediately go jump back to the step where the application or the test case actually failed. That's exactly this activate motor control. So this reaction block did not happen. So I ran into a timeout. That's exactly what I see here. So UART send dump came, but not the control active block. It ran into a timeout. So that's the idea. So if I want to retest it, I just rerun it after I fixed the bug, for example. Now it's green again. So now that's the idea for the test execution. And really in the background, the complete motor control, the motor simulation ran, all the bus systems, the temperature simulation, and so on. So, but now I want to to test a little bit deeper my variants. So for example, I want to test all the, I'm making this a little bit smaller so that we can, it's for example, I want to test more variants, and I want, for example, variant 1 to test for all the speeds, and also for variant 2 and all those paths through my application. So now I can start to add more variants. So for example, the variant configuration would change the data on my system under test and set the parameters for my test system. This needs to go hand in hand. So let's say I have 4 variants. I want to test for all the equivalency classes and all those change direction, break, and whatever functionality I want to test. Now I need to up the stakes here a little bit. For example, I do not get away for those combinations with 8 test cases. So let's add more deeper test coverage here. So now I add the combinatorial test case generation for those test cases. I regenerate the C code and the documentation. Now I go back to my documentation here. You can see I have 4 variants, and now suddenly I need to cover all those paths. I need 60 test cases here, and they're all automatically generated. Here you can see every path here through this graph is a test case. And on every edge, on every transition, a test step or a test sequence is executed to check whether this step works or not. So now let's really search for race conditions. I make the test much deeper now. I can easily go up to 10. It doesn't really explode, but of course, I will generate much more test cases now. Now let's have a look what those test cases look like. And let's go back here to my documentation. That's easier than to look at the code. Now, again, the variant test cases, but in this case, now I have something like a couple of 100 test cases or so. Let's have a look at this. That's 258 test cases I need to cover this. You see, you get more test cases, but it doesn't really explode. It's a very nice metric we have here. And you find lots of race conditions and sporadic errors by doing this. But you need to find the steps and the sequences before you start with those combinations, because of course you need to execute some tests while you're doing this. So last but not least, I can run the complete test cases also on a continuous integration server, and also the continuous integration server on every commit, it executes the test cases, and you get also the test reporting completely on your continuous integration server. So if something happens here, you click on the continuous integration server on the graph and you get exactly the position where your system failed or where you want to get to the implementation of your test case. Okay, so that's it for now. If you have any questions, don't hesitate to contact either Michael Weiss at Hitex or myself. And yeah, I hope this was interesting for you.